Here are the exact parameters of Leetcode 921, minimum add to make parentheses valid. You receive an input string of opening and closing parentheses. Your task is to calculate the minimum insertions required to make it valid. A valid string is strictly defined by nested matching. Every opening bracket must have a subsequent properly nested matching closing bracket. To solve this efficiently, we will map the logic to a last-in, first-out memory model, compress the space complexity to a mathematical constant, and prove it on a manual trace table. Mastering the optimization and manual proof of this problem solidifies the mental discipline required to track state through nested dependencies. Parentheses validation is a history problem. An opening bracket creates a structural debt. That debt must be paid by a matching closing bracket in the future. To track this debt, we need a data structure that remembers the most recent unresolved item. We use a last-in, first-out, or a LIFO stack. Watch this vertical array. The moment we encounter an opening bracket in the string, we immediately push it into memory. As the scanner continues, it hits a closing bracket. This resolves the debt, canceling out and popping the top opening bracket from the stack. The primary edge case occurs if the stack is empty when we encounter a closing bracket. That creates an orphaned state, a bracket that needs an opening pair we never saw. Once the entire string is processed, any brackets left inside the stack, combined with any orphaned closing brackets we counted, equal the exact minimum insertions required. The standard stack approach works, but it requires proportional O of n auxiliary space to store characters in memory. Look closely at the physical constraint of this specific algorithm. The array we built only ever holds one uniform type of character, the opening bracket. By dissolving the physical array, we apply O of 1 space compression. We replace the memory allocation with a single integer counter named open needed to represent the stack size. Next to it, a second integer variable, close needed, tracks orphaned right brackets hitting our zero-state virtual stack. This variable substitution eliminates the need for dynamic memory allocation while preserving the original logic, reducing the auxiliary space used to a fixed constant. With the logic optimized, you now have to prove it works without relying on a compiler. The biggest trap in an interview is reading your code instead of running it. When you visually skim, your brain projects intended logic. You must execute mechanical state changes blindly. This grid is a trace table. It forces you to store system state on paper, freeing your working memory to process the logic execution. Let's run the trace on the edge case string, index 0, opening bracket. We update the open needed column from 0 to 1. Index 1, closing bracket. This pays our debt. The table advances, and open needed drops back down to 0. Index 2, another closing bracket. The logic checks open needed. It's 0. We have an unmatched bracket, triggering the close needed column to increment to 1. Index 3, a trailing opening bracket. The table advances to the final row, and open needed increments back to 1. The loop terminates. The final state of all system variables is locked inside this highlighted row. Looking at this equation drawn directly from the trace table's final state, we calculate the required additions. 1 plus 1 equals 2 insertions. Because we parse the string exactly once from left to right, our time complexity is strictly O of n. And as these metrics show, our physical memory is constrained to just 2 integer variables, regardless of the input size, yielding a space complexity of O of 1.
So initially, we create 2 integer variables, open and close, assigning both values as 0. Then we loop through the string s, accessing each character in the variable ch. If the character is an opening bracket, we increment open by 1. Otherwise, we check if open is equal to 0. If it is, we increment close by 1. Otherwise, we decrement open by 1, as we have found the matching closing bracket for an opening bracket. Finally, we return the sum of open and close.